The screen opens to a vast, silent darkness. Not the comforting black of a night sky, but something deeper, an abyss so wide that even starlight seems reluctant to cross it. Slow ambient music swells, and then a calm, authoritative voice begins to speak. "I'm Michio Kaku," he says, stepping into view against a shimmering backdrop of galaxies stretching like glittering veins across the cosmos. And today, we're going to explore a question humanity has asked for decades. What truly exists inside the universe's vast empty spaces? Are they really empty? Or is something extraordinary hiding in the dark? He walks forward, hands clasped behind his back, as the camera glides through a three-dimensional rendering of the cosmic web. When astronomers first mapped the large-scale structure of the universe, he continues, they discovered something astonishing. Galaxies do not scatter randomly like dust blown across a table. Instead, they gather along immense filaments, cosmic highways of matter, stretching for hundreds of millions of light years. Between these filaments are enormous dark basins, wide as intergalactic oceans, called cosmic voids. The camera dives into one of these voids. Nothing but darkness, no stars, no planets, no glowing nebulae drifting like cosmic lanterns. At first, Michio says, we believed these voids were true vacuums, great hollows carved into the universe by chance, utter nothingness on a scale too immense to comprehend. He stops walking. The view around him freezes, expanding outward to reveal a bubble hundreds of millions of light years across. But new research, he says with a subtle smile, has shattered that idea. We now know that even the emptiest regions of the cosmos are not empty at all. In fact, they are alive, with particles, radiation, and the faint fingerprints of forces that shape everything we see. A faint blue glow ripples across the void. Tiny dots, subatomic particles, shoot through space like ghostly sparks. Inside every cosmic void, Michio continues, there are invisible particles drifting through the darkness, relic radiation from the dawn of time, and delicate threads of dark matter weaving through the emptiness. So even in regions where galaxies are scarce, the universe still whispers, still vibrates with energy and motion. The view shifts again, zooming into a miniature simulation of a single cubic meter inside a void. Tiny flashes appear at irregular intervals. One of the most active travelers across these dark deserts, he says, are cosmic rays, high-energy protons and nuclei born in places of unimaginable violence, exploding stars, colliding neutron stars, and the jets of supermassive black holes. These particles move at nearly the speed of light. When they pass through the emptiness of a void, they create faint signatures, like sparks crossing an endless ocean. The camera tilts upward, showing streaks of light racing across the frame. But even cosmic rays cannot match the ghost-like nature of another particle, neutrinos. These nearly massless particles stream through the universe in unimaginable numbers. Millions pass through your body every second, and yet you never feel them. They pass through planets, stars, entire galaxies as though they were smoke. A single neutrino glides silently through the screen. If you could float inside a cosmic void with a sensitive detector, Michio says softly, you would feel these neutrinos passing by in a constant gentle whisper. The void is quiet but never silent. He raises a hand and the scene shifts again, revealing a faint grid-like structure. And then, he adds, there is the mysterious substance that shapes everything, the invisible backbone of the cosmos, dark matter. The camera zooms out, showing how dark matter clings to the edges of the void, forming faint halos that cradle galaxies like pearls strung along invisible wires. Dark matter does not shine, it does not reflect, but its gravity is powerful enough to sculpt the universe itself. Inside a void, dark matter determines where galaxies cluster, where they gather, and how they form. Even in the quietest corners of space, dark matter is there, gently shaping the contours of emptiness. Another transformation, the darkness becomes bathed in the faint red-orange glow of the cosmic microwave background. And surrounding everything, Michio says, is the oldest light in the universe, the cosmic microwave background, the afterglow of the Big Bang. This radiation fills every inch of space, even inside the most remote voids. It is cold, just 2.725 Kelvin, barely above absolute zero, but it ensures that the universe is never completely dark, never completely lifeless. He steps closer to the camera, lowering his voice. So while cosmic voids may look silent and barren, they are actually alive with motion, a place where the universe's oldest light and its fastest particles drift endlessly through the dark. The music deepens, building a quiet tension. But this raises a profound question, Michio says. Why does the universe have voids at all? Why isn't matter spread evenly? Why are there these gigantic empty basins surrounded by brilliant filaments of galaxies? He turns and the cosmic web appears again, filaments glowing like bright rivers, voids stretching between them. To answer that, he says, scientists had to study these voids not as empty regions, but as cosmic clues. Because the distribution of matter, where it gathers, where it avoids, tells us something extraordinary about the forces that shape the universe's birth and evolution, he pauses. And what we discovered, he says, is that voids may hold the key to understanding dark energy, the mysterious force accelerating the expansion of the universe. A sudden pulse of light expands outward, mimicking cosmic expansion. In dense regions, gravity wins, stars pull together, galaxies collide, matter gathers. But in the near emptiness of voids, something else dominates, dark energy, a force pushing space itself apart. Michio walks slowly across a dark plain filled with glowing points of matter drifting apart. In these vast empty basins, the influence of dark energy becomes clearer, stronger, almost pure. Studying how voids expand over billions of years may reveal whether dark energy is constant or evolving, or even something far stranger than we imagine. He stops walking. The cosmos shifts behind him, revealing a close-up of the cosmic microwave background with tiny distortions. And cosmic voids, he says, also help us test Einstein's theory of general relativity. As light from distant galaxies travels through these underdense regions, it stretches and cools, losing a tiny bit of energy in what we call the integrated Sachs-Wolf effect. It's a subtle phenomenon, but it allows us to test gravity itself across billions of light years. He lifts a finger. Einstein said that gravity is the warping of space-time. Void studies allow us to check if that's still true on the largest possible scales, or if the universe is hinting at a new kind of physics. The music softens. And so, Michio says finally, what began as empty space has become one of the greatest natural laboratories in the universe, a place where we can study expansion, dark matter, neutrinos, and the very fabric of space-time. With almost no interference from stars or galaxies, he looks directly at the viewer. In the deepest darkness, he says, we find the universe speaking most clearly. The camera slowly fades out into the silent black of a cosmic void, pulsing faintly with ancient radiation. The screen brightens again as Michio Kaku steps into a sweeping panorama of the cosmic web, each filament glowing like strands of illuminated silk. In the last segment, he begins, we uncovered the astonishing truth that cosmic voids, these vast silent basins stretching across the universe, are not empty at all. They are alive with particles, radiation, and invisible forces, but that was only the beginning. Now we dive deeper into how these voids shape our understanding of the universe. Because inside the darkness, the laws of physics reveal their most subtle secrets. The camera zooms forward, slipping past galaxy clusters and plunging again into a void. To truly study a cosmic void, Michio says, we first needed to understand the cosmic web itself. This web is not just a pattern, it is the architecture of the cosmos. Filaments form where dark matter creates gravitational valleys. Matter flows along these valleys, gathering into stars, galaxies, clusters, and in between these structures, gravity weakens, energy dominates, and space becomes underdense. Those regions expand faster than the rest, and that is what creates the voids. He lifts his hand as the void expands outward, like a balloon inflating. But why does this matter? Because in these regions, the delicate balance between gravity and dark energy becomes crystal clear. The camera pans to a simulation showing two regions side by side, a dense galaxy cluster and a nearly empty void. In galaxy clusters, gravity overwhelms. It's chaotic. Matter collides, orbits, collapses. Trying to decipher the influence of dark energy in such a crowded environment is like trying to hear a whisper during a hurricane. A soft breeze-like sound plays as the scene shifts into the void. But in a cosmic void, he continues, gravity is faint, almost silent, and in that silence, dark energy becomes audible. Its push becomes measurable. The universe expands faster inside voids, and by measuring that expansion, we can test whether dark energy is constant or whether it's changing. He walks through the dark basin as faint white grid lines stretch outward, expansion visualized in slow motion. If dark energy were to strengthen over time, Michio says, voids would expand more rapidly as the universe ages. If it weakens, their growth would slow. And if dark energy is not a property of space at all, but something else, perhaps a field, a new force, voids would betray that truth, because they are the cleanest stage on which the universe performs its most subtle acts. A sudden ripple distorts the background image, as though space itself is warping. But voids do more than reveal dark energy. They also help us test gravity and challenge Einstein's greatest theory. The camera shows a beam of light traveling across billions of light years, passing through clusters, filaments, and finally a void. As light travels through dense regions, Michio explains, gravity pulls on it. It gains energy, falling into gravitational wells, and loses energy climbing out. But in voids where matter is scarce, the gravitational wells are shallow. Light passing through them experiences a small but measurable energy shift. This is the integrated Sachs-Wolf effect. Lines appear tracing the path of photons across the void. When we measure those tiny changes, just a few millionths of a degree in the cosmic microwave background, we're not just observing light, we're observing the interplay between gravity and cosmic expansion over billions of years. It is one of the most delicate tests of general relativity ever devised. The camera shifts again, now focusing on distant galaxies, their shapes subtly warped. And then there is dark matter, he continues. Even in voids, it leaves fingerprints. Its gravitational presence bends the light of distant galaxies, stretching and distorting them. We call this weak gravitational lensing. And by studying those distortions, those faint tug marks in the fabric of the void, we can map where dark matter hides. A three-dimensional fog of dark matter illuminates around the void's edges. This mapping tells us how dark matter behaves in low-density environments, because if dark matter interacts differently in emptiness than in crowded regions, the universe will reveal that difference in the shapes of voids themselves. Michio pauses, letting the imagery fade into the soft glow of the cosmic microwave background again. But perhaps one of the most fascinating connections is between voids and the relic radiation of the Big Bang. The cosmic microwave background washes through these voids as a faint, ancient glow. Though it is cold, just 2.725 Kelvin, it carries the universe's oldest memories. And as these photons pass through the underdense regions, their energy shifts ever so slightly. A small blue wave radiates outward, representing the CMB cooling as it leaves the void. These tiny temperature differences, Michio says, help us trace the depth, shape, and evolution of voids. It is like using the universe's first light as an X-ray. He continues walking as the scene shifts to a digital lab simulation. And yet, he adds, there is another particle revealing secrets in the darkness, neutrinos. Countless ghostly white particles drift silently across the screen. Neutrinos shape the universe in ways we still struggle to comprehend. Their tiny masses influence how matter clusters. And cosmic voids provide one of the best ways to measure that influence, because the size and shape of voids change depending on how neutrinos flow across the universe. The imagery widens, showing how voids evolve from small cavities to enormous basins over billions of years. If neutrinos were heavier, Michio says, voids would grow differently. If they were lighter, the patterns would change. By comparing the observed structure of voids with simulations, we can estimate neutrino masses with incredible precision, far beyond what particle accelerators can measure. He looks up toward the swirling cosmic web. All of this brings us to one final role of cosmic voids. They are now one of the best arenas to test modified gravity theories. Some physicists believe that dark energy is not a force, but instead a sign that our understanding of gravity is incomplete. If gravity behaves differently in low-density environments, if it weakens or strengthens, voids would reveal it. The visual shifts to galaxies drifting around the edges of the void. By measuring how galaxies move near void boundaries, we can test whether Einstein's equations still hold. And if they don't, then cosmic voids may be pointing us toward the next revolution in physics. The music deepens with a soft, resonant pulse. So you see, Michio concludes softly, these immense dark basins are not just empty spaces. They are windows into the universe's deepest truths. He steps aside as the camera glides outward, the void shrinking until it becomes a tiny speck inside the vast cosmic web. In the darkness, he says, the universe reveals what it is made of, how it evolves, and perhaps even what its ultimate fate might be. He faces the viewer directly. And in our final segment, we will explore what lies ahead, how the next generation of telescopes and surveys will illuminate these cosmic deserts like never before, and why understanding nothingness may be the key to understanding everything. The screen fades gently into a field of drifting galaxies preparing for the next act. The screen fades in with a slow drift through a dark expanse, a cosmic void stretching endlessly in every direction. Then Michio Kaku appears again, standing against a curtain of faint starlight. His tone is calm, reflective, yet filled with a quiet sense of awe. In the last segments, he begins, we explored what fills these enormous cosmic voids, particles, relic light, dark matter, and how they allow us to test some of the deepest mysteries of physics. Now, we look forward. Because studying these voids is not just about understanding emptiness, it's about understanding the future of cosmology, the fate of the universe, and our place within it. He gestures upward, and the screen brightens with sweeping visuals of next-generation observatories. Over the next decade, he says, projects like DESI, Euclid, and the Vera C. Rubin Observatory will give us the most detailed three-dimensional maps of the universe ever created. These instruments will chart millions of galaxies, allowing us to trace the shape, size, and evolution of cosmic voids with unprecedented precision. What was once a rough sketch of the cosmic web will become a high-definition blueprint. A simulation plays. Galaxies plotted one by one until a glowing, intricate web forms in astonishing detail. With these maps, Michio continues, we will watch voids grow over time. We'll measure how fast they expand, how their boundaries shift, how they respond to dark energy. Each void becomes a data point in a vast experiment conducted across billions of light years. The camera dives into one of these digital voids, revealing subtle variations in density. And because voids are so clean, so free from the complex interactions found in galaxy clusters, they give us clarity. If gravity ever deviates from Einstein's predictions, if dark energy ever changes its behavior, if dark matter has hidden properties we've missed, the signs will appear most clearly there, in the silence of these cosmic basins. He walks slowly as the music softens, almost meditative. But beyond the science, there's something profoundly philosophical about voids, something that challenges the way we think about the universe. For centuries, humans imagined emptiness as nothing, a perfect vacuum, a blank canvas. But the more we explore, the clearer it becomes. The universe has no true nothingness. Even in the darkest corners, something persists. Particles, fields, gravity, the faint warmth of ancient light. The screen fades to a soft blue glow of the cosmic microwave background. If you could float inside a void, he says gently, the nearest galaxy would be a pinprick of light millions of light years away. You would see no stars, feel no warmth, hear no sound. Yet, you would still be immersed in the relic glow of the Big Bang, washed constantly by radiation older than every galaxy in the sky. You would feel the whisper of neutrinos passing through you, and you would drift through the invisible threads of dark matter that helped shape the universe long before Earth ever existed. A faint hum echoes, symbolizing the CMB's presence. That realization, Michio continues, changes how we think about existence. Cosmic voids are not blank spaces between things. They are part of the cosmic fabric. They help hold the universe together. They influence the expansion of space. They shape the behavior of galaxies. And they remind us that even in the vastness between stars, physics never sleeps. The universe is always moving, always expanding, always whispering information to anyone who knows how to listen. He turns, looking directly into the camera. And perhaps most inspiring of all, studying these voids may help us understand the ultimate fate of the universe. If dark energy continues to accelerate cosmic expansion, the voids will grow larger and larger. Galaxies will drift apart until their light can no longer reach one another. The night sky will empty, the cosmic web will thin, and the universe will become dominated by the same quiet darkness we see inside voids today. A slow zoom reveals a future universe, sparse, silent, stretched thin. In a sense, he says, voids give us a preview of tomorrow, a look at what the cosmos may eventually become. Not a universe packed with galaxies, but one where isolation reigns, where distances grow without limit, where the remaining islands of matter drift in an ocean of darkness. He closes his eyes briefly, as if contemplating that distant future. But even then, he says softly, even in a universe that becomes mostly empty, the lesson we learn from cosmic voids will remain true. Emptiness is never truly empty. There will always be radiation, always be particles, always be the subtle fingerprints of physics etched into space. The music swells into a gentle, uplifting chord. And so, he concludes, as we continue exploring these vast silent regions, we're not just studying nothingness. We are uncovering the hidden architecture of the cosmos. We are learning how matter flows, how energy behaves, how gravity shapes reality. In the darkness, we discover the rules that govern everything. He smiles warmly. Thank you for joining me on this journey, he says. In the emptiest places, we've found the universe speaking in its quietest voice, a reminder that even nothing is something, and that the cosmos still has countless secrets left to reveal. The screen slowly fades to black, leaving only the soft echo of distant cosmic radiation lingering in the silence.